Okay, this is IM1, and this is lesson 5-6. So we're going to be talking about sequences. So let's make a sequence. So let's say we start with 5, and then the next number in our sequence is 10, and then the next number in our sequence is 20, and the next number in our sequence is 40, and the next number in our sequence is 80. So I'm going to ask what's going on. And if you were in the classroom, we could talk about it. And what you would tell me is that we're multiplying times 2, right? We're going times 2, times 2. We're taking this number and we're saying times 2. Taking this number and we're saying times 2, right? We have some starting number and then we're multiplying it by 2. So this is what's called a geometric sequence. What if we wanted to write this as a formula? All right, so let's write it as a formula. So we might need to define some stuff, right? A geometric sequence, we're going to define in a few minutes, but I'm going to tell you this is a geometric sequence, and let's talk about it. So the first number, so I'm going to call this A1, okay? That's the first one in the series. The first one in the series is 5, and it's not times anything, right? So then the next number in the series, we'll call it A2. That's 5 times 2. All right, that was this one. In fact, let's just label these as we go. A1, A2, A3, A4, A5, and we can dot it like it was going to keep going on. All right, let's do A3. A3 is 5 times 2 times 2. Okay, we could also say that that's 2 squared. So 5 times 2 squared. All right, well, this one is a 4, which was 5 times 2 times 2 times 2. So that's 5 times 2 to the third. All right, what if you had to describe the next one? How would you describe that? Well, it would be a 5 is 5 times 2 times 2 times 2 times 2, right? Or 5 times 2 to the fourth. Let's back up for a second, right? What could we put here? Well, actually, we could say this is 5 times 2 to the first power, right? 1 power of 2, that's just 2. I'm wondering, could you even go one farther back? This is a little bit of an advanced concept, but you guys are smart. In fact, this would be actually 5 times 1. Is there a way that we can make 2 to an exponent that's equal to 1? And actually, yeah, we can. We can say it's 5 times 2 to the 0 power. All right, so if we wanted to write 2 different definitions for this, I'm going to call these definitions. The first one, it's called a recursive definition. All right, the recursive definition is basically how you would describe it to me. So take the number before and multiply it. All right. We are going to say, we're just going to let A1 equal A. So A1 equals, or A equals A1, right? So we're going to take the number before that number. In math, we use the letter N to represent some number, but not like a variable in the same way, more like a counting number. So some specific item. Right? X is our number where we can put anything in and it's a variable. N is sort of like, I don't know, the 10th one, the 20th one, the 17th one. And minus 1 would be the one before the one we're talking about. That's sort of what we use N as, all right? So if we were doing a recursive definition, we're basically trying to write out in math, take the number before and multiply it by something, whatever that number is, okay? So in this case, we're going to say that R is equal to the multiplying part. Okay, and in our case, in our example, R would have been 2. And A is going to be whatever the thing we started with is. All right, so for anything after A, or anything after A1, we can say that our value, and we're going to call that A to the nth power. That means any value in our sequence is equal to the one before it times R. All right, that's a recursive definition. You might need to play this a couple of times to get that concept because it's a weird concept. But what we're saying is the one before, so any number in the sequence, any number in the sequence is the one before times whatever we're multiplying it by. All right, we're going to do one more definition, and we're going to call it the explicit definition. I think I have enough room to split it in here, okay? So I'm going to draw a little line so you can keep track of where I am. And we're going to use the same letters as we used before. Okay, so our explicit definition is without knowing the one before. Right? If I said I want you to find the 25th number in this sequence, but you don't know what the 24th is, right? The explicit definition will give it to you because it will help you answer it without knowing the one before. It's our single formula. All right, and here's what we can do. We can say, look at this exponent. This exponent is always going to be the one that comes before the sequence. So for the third sequence, right, the third item in the sequence, we're going to have the exponent of 2. For the fifth item in the sequence, we're going to have the exponent of 4. All right, so we're going to write it like that. So for any object in the sequence, any number in our sequence is going to be equal to our starting number times our multiplying portion minus 1, right? So if we want the 45th, that's going to be a huge number. So let's do the 14th. So if we want the 14th in the sequence, right? So we want A to the 14th. In our number sequence, that's going to be 5 times 2 to the 1 less than 14 to the 13th. P.S. That's going to be a huge number, but we'll do it, all right? So 5 times 2 to the 13th is equal to 4,900 I just combined those two letters, 60.